Greetings, welcome to lecture number 39 on basic circuit theory. I am Razavi. Today we will continue to look at various circuits that use op-amps to perform interesting and useful functions. These circuits include the non-inverting amplifier, the inverting amplifier, and the adder circuit. So before we go there, let's just take a quick look at what we discovered about op-amps last time. We said that an op-amp is a strange creature. It has two inputs and one output, and each of these inputs can receive a voltage with respect to the reference, with respect to ground. So we call these V-in1 and V-in2. And we saw that the op-amp has two inputs, which we denote by a plus sign here and a minus sign here. And these two inputs are distinctly different, so we cannot swap them. So we called this input the non-inverting input, and this one the inverting input. And what the op-amp does is that it always looks at the difference between these two and amplifies it by some factor, which we call the voltage gain. So the voltage gain determines how large the input is for a given difference between the two inputs, how large the output is for a given difference between the inputs. All right, now we saw that in practice, with typical values that we have for this Vout, so let's say at most 10 volts or something for off-the-shelf op-amps, this difference cannot be very large. So it's a good approximation to start out our analysis of a given op-amp circuit by assuming that these two inputs are close to each other. They're not exactly equal, but they're close. And then one other simplifying assumption that we make is that these two wires going to the op-amp do not draw any current. So we say that the input currents are zero. With these two assumptions, analyzing op-amp circuits becomes very simple and very intuitive. And in fact, when we design circuits that use op-amps, we would like this condition to hold, because otherwise it's not a good design. So we started by building these little circuits, and the first circuit we saw was the unity gain buffer. And it was obtained simply by taking, so this is our unity gain buffer. So we took an op-amp like that. So here's our op-amp. And we have an input voltage here, which we call V-in. And we took the output of the op-amp and returned it to the input. And by that we mean we just connected the output back to the inverting input. So we brought this back and connected it here. And we call this V-out. And of course, when we say V-in, this is measured with respect to common reference. There's a ground here. And the op-amp has its ground as well. Remember, there's a voltage-dependent voltage source in here, and that is connected to this point. And V-out is also measured between here and here. And this wire just goes over this wire. Okay, so we analyze the circuit by observing that these two inputs of the op-amp have approximately equal voltages. So if this is my input and it's called V-in, then this one should be also close to V-in. So we say this is approximately equal to V-in. And because the output is just shorter to this input, the output is also approximately equal to V-in. So we say this is a unity gain circuit because you can see that the voltage gain is 1 as I go from the input to the output. If I put this in a black box, and I ask you, how much is the voltage gain? You say it's about 1 because all of the input went to the output. All right? Now, why the circuit might be useful is beyond the scope of this course, but yes, in some cases we do use this unity gain buffer. Okay, then we went to something a little more interesting, which we call the non-inverting amplifier. And in this case, we did we built the circuit a little differently. So we said, okay, we'll start with the op-amp and an input voltage. So So here's our op amp, and we have an input voltage. I will draw this sometimes as a complete voltage source, or sometimes as this. It's the same thing, right? And then what we did is we took the output, Vout, but we did not return all of Vout to the input. Just like here, rather we divided this down by means of a resistor ladder or resistor divider, R1 and R2. We know that this circuit divides the voltage, right? So these all go to ground all together. So we have this here and this here. And, oh, sorry, not this one. This input we need. The op amp has its own ground connection. Now we divide the output voltage using these two resistors, and we take the result and bring it back and connect it to the inverting input of the op amp. So this goes right here. So this is what's called a non-inverting amplifier, and we will see in a moment why we call it non-inverting. Okay, so our objective is to understand the circuit, to analyze it, see how Vout is related to Vin. Presumably it's an amplifier. We just have to see how much gain it provides. What's the ratio of Vout to Vin? All right, so as long as we remember these conditions, the analysis is actually very simple. So those are the key. Those are the idealization that we have made for this box so that we can readily write the solution. Okay, well, let's go and sit right here and ask, if this voltage is Vout with respect to ground, how much is this voltage here? So I'm going to call this node X right here. And I'm asking myself, how much is Vx? So I say Vx is equal to, this is a voltage divider, right? I have two resistors dividing this voltage. So if this is Vout, this would be R2 over R1 plus R2 times Vout. So this voltage at node X is R2 over R1 plus R2 times Vout. Okay, so that's great. Now there's one assumption here that we have to be careful about. This circuit divides this voltage by this value if there is no additional current going this way anywhere, right? If this had some current, the equation would be wrong. And given the assumption that we have made, it's okay, right? We have assumed that this input of the op amp or this input of the op amp draw no current. So indeed, the voltage from here to here, the voltage divider equation is just this, what we've seen in the past many times. Okay, so we got this voltage for Vx. All right, in the next step we say, we know that the two inputs of the op amp have approximately equal voltages. So if this voltage is called Vin, this voltage should also be called Vin approximately. So this voltage is also approximately Vin. And of course this voltage is nothing but Vx, because Vx connects to the inverting input of the op amp. So Vx is equal to Vin approximately. So I can say that this is equal to the input. Let's see if this pen sometimes doesn't work here. Let me try the other pen, see if that one works. Okay, so we know that we have this Vx, and Vx happens to be equal to Vin, so we say this is, right, let's see here. This is equal to Vin. Okay. All right. So now I can find Vout, right? Because I have this equation. So let's go ahead and do that. I have to multiply by R1 plus R2 divided by R2. So what I see is that Vout is equal to 1 plus R1 over R2, R1 over R2 times V in. This is the equation that tells us the behavior of the non-inverting amplifier. And it teaches us so much about what this circuit does. All right, so we'll examine this result bit by bit. All right, so that's what we have obtained for the output voltage of the non-inverting amplifier. We can also say that the voltage gain of the circuit, meaning the output divided by the input, is just this much, right? So we can say gain, and by gain we mean voltage gain, is equal to 1 plus R1 over R2. So for example, if R1 over R2 is 9, then the output voltage is 10 times the input voltage. So if this microphone signal has a peak amplitude of, for example, 1 millivolt, the output of the amplifier will have a peak amplitude of 10 millivolts, right? That's what we mean by voltage gain. Okay, so we have this result now. All right, so we'll examine this from different perspectives and make a bunch of observations. So let's write that here. Okay, so number one, we call this amplifier non-inverting because the output and the input have the same sign, as you can see here, right? So we say V out has the same sign as V in, so we call this a non-inverting amplifier. And this distinction is made because a little later we're going to talk about the inverting amplifier, and that inverts. It multiplies the input by a negative sign as it goes to the output. Okay, so that's pretty simple. Point number two. What we see is that, remember we said this op-amp has some gain? Remember we said that this output is actually A0 times V in 1 minus V in 2? Is that A0 does not appear in this equation, right? So we see A0 does not appear in the result. And neither does the op-amp equivalent circuit. Remember I showed you the equivalent circuit last time, and I said there's a voltage dependent voltage source in here. We never needed that for our analysis. Why? What happened? Well, it's because of these two assumptions. When we make these two assumptions, essentially we are assuming that the op-amp gain is infinite. Okay, we didn't talk about that much, but that's what it really means. And also the input currents are zero. So when we make these two assumptions, we avoid the use of the complete op-amp model and this equation. So the result is much simpler to obtain, and there's also much more intuitive. Okay, so that's the value of making these two assumptions. Okay, now the next point to consider is the following. So what happens if R1 goes to 0? We have this equation, right, for the output in terms of the input. So one simple question would be, let's consider some extreme cases. R1 is 0 or infinity, or R2 is 0 or infinity, and see what we can, how we can explain the result. So this is the quiz of the day. I will give you 1 minute to think about it. All right, so what did you decide? Well, this equation says that R1 is 0, so V out is just equal to V in, just like the circuit here. So why is it that when R1 is 0, this circuit behaves like this one? Well, let's try to draw the circuit when R1 is 0, see what we get. So here's the situation. We have our op amp, we have a 0 resistance, so that's a short circuit. And then we have resistor R2, which goes to ground. And then we have this this connection here. And we have this V in here. That's the V out. So does this circuit behave like this one? The only difference between the two is this resistor, which is connected from this output to ground. Does this resistor change the behavior of the circuit with respect to this one? And the answer is no. Why? Well, remember what's inside this op amp. It's an ideal dependent voltage source. So if I draw that quickly, what I remember is like this, right? That's the voltage source that we have inside here. And that voltage source is driving this R2. And then we go this way to the input, right? So even though we are not using the equivalent circuit of the op amp, it's still good to remember what the equivalent circuit looks like so that we can understand intuitively why this R2 has no role in the circuit. Well, you can see that because it's an ideal voltage source, the voltage here is always defined by this voltage source, regardless of the value of this resistor, so long as it's not 0, of course, right? So we see that this resistor plays no role in the output of the circuit in this topology, in this particular case, simply because it is in parallel to a voltage source. All right? So this circuit is identical to the circuit as long as the op amp is ideally modeled by this voltage-dependent voltage source. All right, let's consider another case, which is also interesting, and see what happens if R2 goes to infinity. This resistor goes to infinity. So we'd like to analyze that situation and again try to explain the results intuitively. So if R2 goes to infinity, this equation tells us that V out is equal to V in. So let's draw the circuit and see what it looks like. When R2 is infinity, here's the situation. We have our op amp sensing V in, and then R1 is still there. We didn't change that. But R2 is infinity, so it's an open circuit, right? We throw away R2, we just keep R1. So here's what we have. V out. So that equation on top says that in this case, again, the gain is 1. V out is equal to V in. So it's saying that this circuit behaves the same way as this circuit. Why is that? Why does R1 have no role in this particular topology? Well, remember that we said the op amp draws no currents, right? So the current through this is 0. So we say I is equal to 0. If the current through this is 0, the current through R1 is 0. If the current through R1 is 0, the voltage across R1 is 0. So this voltage here is 0. If this voltage is 0, whatever voltage we have here, we have here. So this is still equal to V out. And the op amp wants to make sure that these two are approximately equal, so V out is still equal to V in, just like the previous case. So even though we have inserted a resistor here, R1, the relationship does not change so long as this assumption is valid. All right, so these are interesting extreme cases that give us a better understanding of what the op amp does. All right, the next point that I wanted to make relates to what we call feedback. So we want to understand the notion of feedback and in particular see how the op amp is providing feedback. So we're going to call this feedback. So we say this circuit incorporates feedback. And by that, we mean that we take the output and we feed it back to the input. You see this network here, or this network here. So we need that concept because it's a very useful concept. If you have taken control systems, you've seen it before. If you haven't, that's okay. So the idea is that we take the output generated by this op-amp, we pass it through some sort of network, and we bring it back to the input. That's called feedback. So conceptually, we're going to do it like this. We take the output, pass it through something. We don't know what it is, just some blob, and then we return the result here. And this is called feedback because the output is fed back to the input. Okay? Now we'll be even more specific. We will say this is negative feedback. By negative feedback, we mean that the output, which went through this blob, through this circuit, and came back to the inverting input of the op-amp, not the non-inverting input of the op-amp. This is extremely critical because if we accidentally bring this to the positive input, not the negative input, the circuit won't work as expected. All right, so that's extremely critical. You can see here that the feedback is back to the inverting input. Here's back to the inverting input. In general, for the circuits that we're studying here, it's always going back to the inverting input. So that is always, that's an example of what we call negative feedback. All right, so that's another key concept that we have here. There is a tremendous interest in being able to read the brain waves. The waves that are created by our brain while it's working show a great deal about what's happening for example, in a patient's mind. And the brain waves are simply voltages that we can sense across the skin on the forehead, as you can see in this diagram, by some electrodes. And the shape of this waveform as a function of time can be something like this, or something like this, or something like this, etc. You can see that if the brain is really busy, for example, you take an exam, then your brain waveform is going like this at a relatively high frequency. Whereas if you are somewhat busy, it's at a lower frequency. But if you're relaxed, if you're resting, and you're not thinking much, then it has even a lower frequency. So by measuring these voltages on the forehead, we can actually see these waveforms. So the question is, how do we do that? How do we measure these voltages? So we can attach all these electrodes and these wires to the head, but then that's very cumbersome. Right, the patient has to sit in some place and we have to attach all of these things. What if we want the patient to be able to move around and still we want to collect the brainwave information? How do we do that? Well, in this paper, they propose a little band that is attached to the forehead and it collects the brainwave information and then wirelessly transmits out. So that's an interesting idea, and by having enough electrodes, enough probes here, enough sensors to measure these activities, they can collect all the information from the patient, and the patient is free to move around. Okay, so the circuit that they use consists of these various building blocks, and I just wanted to point out that what we learned about op-amps proves extremely useful here. You can see that they have these various op-amps here that perform different functions, and the information from this headband arrives here. So that's the input signal coming from the headband, and then is processed by these op-amps. Some of these circuits look familiar. You can see that this is a non-inverting amplifier. This is somewhat like an integrator, maybe a filter. This is again somewhat like an integrator or a filter, etc. So this is another a non-inverting amplifier, and so on. So you can see that op amps have a very wide application in this type of system because we have to measure these small signals and process them carefully, amplify them, filter them, and then send them out for further digital processing. Isn't that beautiful? Okay, now looking at the circuit also, we can make another observation which is interesting. As Vin changes with time, so that's the signal from this microphone, this voltage is going up and down, the op amp is generating this output which is also going up and down, right? So let's say this is 10 times that voltage. And through this feedback, what the op amp is trying to do is ensure that this voltage is close to this voltage. So whatever we apply here, this goes up and down, the op amp says, okay, I need to select this voltage, I need to, so that this node always tracks the input. So if the input wants to go up by 1 millivolt, this also wants to go up by approximately 1 millivolt. If the input goes up by 1 volt, this also wants to go up by approximately 1 volt. So the job of this op amp is to bring this negative feedback signal here such that this voltage of the inverting input is always close to the voltage of the non-inverting input, so that this assumption is always valid. All right, that's what the op amp does through this network. So that's also a key point that we rely on a lot in op amp design and op amp circuits. All right, so let's go and look at some variants. We're going to play with the circuit. We add some twists to it so that we can analyze the circuits as well. So let's go to the next page and look at some twists. Okay, so twists on the non-inverting amplifier. So my objective here is not to necessarily introduce another circuit that's useful, but just play with what we have seen and add things here and there and see how they change the behavior of the circuit, right? So that again, we're comfortable with analyzing circuits that have op amps in them. All right, so here's we're going to start with our standard, not this one. We're going to start with our standard non-inverting amplifier. So R1 here, R2 here. And here's our voltage source, which we call Vin. So Vin goes into the non-inverting input of the op amp, and here's our output, Vout. Okay, so we have analyzed this, we know how it works. Now let's go ahead and add some other stuff in there and see what happens, right? So it doesn't bite, so we can always do that. All right, so the first component I'm going to add here is a resistor here from this input to ground. All right, just for the fun of it. So how does this resistor affect the overall result here? So when I'm writing V out in terms of V in, does RA come into the picture? All right, so let's take a moment and see. And the answer is no, it does not. Why? Well, because RA is in parallel with an ideal voltage source. This voltage with respect to ground is always V in regardless of the value of RA. RA can be 1 mega ohm, 1 kilo ohm, 1 ohm. So long as this is an ideal voltage source, this value is always V in. So once we have V in here, the op amp doesn't care what we have here, right? The op amp says, I take this voltage, multiply it by 1 plus R1 over R2, and produce that at the output. So having RA here does not change the behavior of the circuit, so long as this is an ideal voltage source. All right? Okay. Now let's go and add another twist. I'm going to add another resistor here. call it RB. Does RB change the results? No, because RB is like the resistor we saw before when we replaced R1 with 0. In any case, RB is connected from the output to ground. And we know that inside this op-amp, there is an ideal voltage source. So as long as an ideal voltage source is connected to this node, it wants to impose its own voltage at this node. It does not matter whether we have this RB, whether RB is 1 mega ohm, 1 kilo ohm, or 1 ohm, as long as what we have in here, remember that little dependent source? As long as that dependent source is here and it's an ideal voltage source, RB does not change the results. So again, the results do not change. Okay. All right, one last twist. What if I come along and add a resistor here, call it RC, and I ask for this voltage? So let's call this V out prime. Okay, nothing else is connected, so you don't have anything else here. It's just the resistor sitting, floating in the circuit. What can I say about V out prime in terms of V in? It's the same thing as V out. Why? Because there's no current this way, right? So this current is 0. If this current is 0, this voltage drop is 0, so these two voltages are equal. So V out prime is the same as V out. So these resistors are things that people often add in textbooks and so on, just to make the circuit a little more complex, to trick us and see whether we can analyze these circuits, right? So the basic core is still the same, just added a few things here and there. Okay, all right, so that is what we have for the non-inverting amplifier. The non-inverting amplifier has some amount of gain, 1 plus R1 over R2, 1 plus the ratio of these resistors, right? That's what we need to remember. And of course, the positive gain, because it's a non-inverting amplifier. Now we can switch gears to the inverting amplifier. So let's see how that goes. So the inverting amplifier can be drawn in two different forms. I will draw both. One of them is more common than the other, but we just have to get used to both of them. So one form is like this, where we still have our basic connections as before, like the non-inverting amplifier. And we have this resistor here, R1, this resistor here, R2. This connection is still here, okay? The output is still here. So far, it looks like the non-inverting amplifier, right? But the only difference is that now we don't apply our input here. This input is grounded, and we apply our input here. So we call this V in. All right? That's one drawing that you might see in some textbooks, but the more common drawing is not this. The more common drawing is as follows. So we draw the op-amp, but this time we place the inverting input on top and the other on the bottom. So this, it goes like this. And now we say our input voltage, V in, goes through a resistor R2 to the inverting input of the op-amp. And there's another resistor connected from the output to the input. So another resistor connected from the output to the input, R1. This is V out. And the non-inverting input is grounded. So it's grounded like this. So both of these are exactly the same circuit, but this drawing is much more common than that one. Okay, so again, we would like to understand what the circuit does, find V out in terms of V in, and all the good stuff. Still, remembering those two basic rules. There's no current drawn by the op-amp from these wires, and the two input voltages of the op-amp are close to each other. So whatever we have here, we also have here approximately. All right, and based on that, we should be able to analyze the circuit. We don't need to draw the equivalent circuit of the op-amp with the dependent voltage source in it and all that is pretty simple. All right, so we eyeball the circuit for a moment and then see what we can do here. There's a node here called X, right? This is where R2 and R1 and the inverting input of the op-amp meet. What can I say about the voltage at node X? Well, we see that this voltage is 0, and the op-amp wants to make sure that the other input has approximately the same voltage. So I can say that Vx is also approximately equal to 0. So we say Vx is approximately equal to 0. Again, remember, in a well-designed op-amp circuit, the two inputs of the op-amp have approximately equal voltages. So if one is 0, the other one should also be close to 0. All right? Okay. Now we can go ahead and analyze the circuit, even without worrying about what the op-amp does. And I'm going to draw a simplified version of this. The simplified version is applicable and useful as long as we remember there's an op-amp in here, okay? So the simplified version looks like this. I have my input. Here's my input. Just say V in. Then I have a resistor R2. Then I have resistor R1. Then I have voltage V out. Do you agree with all of this so far? V is connected to the left side of R2. R2 and R1 share a node together. And R1 goes to V out. So far so good, right? And then what we know is that this voltage here, Vx, is approximately equal to 0. This voltage right here. That's what the op-amp does, right? It wants to keep these two voltages equal to each other. So now I have not drawn the op-amp symbol in here, right? I just have this very simple situation, and that's great. I can readily analyze it. I'm trying to find V out in terms of V in. How can I do that? Very simple. We write a KCL here, right? How much is the current going through R2 from left to right? The voltage on the left minus the voltage on the right divided by R2. So this current is V in minus approximately 0 divided by R2. How much is the current going from V out to this point, this current? We can write it like this, or we can write it like that. It doesn't matter, so let's write it this way. How much is this current? The voltage on the left minus the voltage on the right divided by R1. So that would be V out over R1. Of course, both of these are approximations because this voltage is not exactly 0. Okay, so both currents are entering the node. They have to add up to 0. So we go ahead and we say V in over R2 plus V out over R1 is equal to 0. And that tells me that V out is equal to minus R1 over R2 times V in. And this is the equation governing the inverting amplifier. All right? So you can readily see why we call it inverting. See that there's a negative sign here. So for example, if the input voltage goes up, the output voltage wants to go down. Okay, so that's fine, not a big deal. All right, so you can see this methodology for analyzing op-amp circuits is very useful. I am able to simplify this circuit to this, and this is only true because we have an op-amp here, right? This is 0 because we have an op-amp. If you didn't have this op-amp, you could not have a 0 volt value here. It would be different, right? Because you just have two resistors. So, but this simplification greatly helps us write the equations quickly and see what happens. All right. From another perspective, what's happening is that this voltage generates a current through R2, right? That current comes in here. And where can it go? It sees two wires, one going to the op-amp and one going to R1. Now the wire going to the op-amp does not draw any current. That was our assumption about op-amps. So all that is left is this way. The current goes this way, goes through R1, comes to the output. And that's how we generate an output which is given by that equation. So it's helpful to think that because this voltage is close to 0, we have a current equal to V over R2 that comes into this node and then has nowhere to go but through R1, and then it makes it the output and it generates that voltage. Okay, so a few observations for this circuit as well. Now that we know how it operates, so observations. Number one, we see that we have negative feedback. So circuit has negative feedback. How do I know that? Well, I see that I have taken the output signal and I run it through some blob and I returned it to the inverting input of the op-amp, and that's why we call it negative feedback. All right, that's essential. We cannot swap these two. If this comes back to the positive input, and the circuit will not operate as expected. Okay, the next point about the circuit is that Vx, node X, has a voltage close to 0. Right? We decided that because this side is 0, this side is also close to 0. So we have a name for node X, and that name is very common in analyzing op-amp circuits. We say node X is called a virtual ground. Okay, it's not a real ground. Why? Because it's not literally shorted to ground, right? We do not have a short circuit between these two. Rather, because of the negative feedback, because of the op-amp action, we guarantee that this voltage is always close to this voltage. So because this voltage is 0, we call this voltage, this node, a virtual ground. All right, so virtual ground always gives us the impression that the voltage at that node wants to be close to 0, regardless of what's happening. This can be going up and down, this can be going up and down, this voltage still wants to stay around 0. And this brings us to a nice analogy between the inverting amplifier and something that we have seen as children, okay, the seesaw. So, analogy with seesaw. Okay, a seesaw is like this, right? We have a little support here, and we have something like this, right? And one child sits here, one child sits here, and they go up and down, right? That's the seesaw. Okay, so imagine that the two arms of the seesaw are not equal. So for example, this is short and this is long. Now what happens? If I press on this and this comes down by some amount, what happens to this one? This goes up by a larger amount. So a small displacement here translates to a large displacement here. And that's exactly what's happening here. If this goes down by some amount, this goes up by a larger amount because they are related by this equation. If R1 is greater than R2, so let's say R1 is 10 R2, then if the input voltage goes down by 1 millivolt, the output voltage wants to go up by 10 millivolts, just like this. So a small displacement on this side gives us a large displacement on that side. So that's a nice analogy to remember. This point does not change, just like this voltage here. This voltage is fixed, right? It's just that these two have displacements in proportion to the lengths of these arms, which sort of look like these resistor values. All right? Okay, let's see. And the next few points that we have for the circuit. All right, so again, let's add some twists to the circuit and see how it behaves. So some twists just for the fun of it. So I'm going to add some devices and so on and see what the circuit brings us. So here I'm going to draw the circuit again. So here's our input V in going to R2, then going to R1, and this is the output, V out. Okay, that's our basic inverting amplifier. Now I come along and I introduce a resistor here to ground, and I call that RA. So the question is, does RA change the behavior of this circuit? So we have to think about it a little bit. This is tricky. This is interesting. Okay, well, maybe I can go back to this circuit here, right? And this is a simplified version of this, or simplified version of that. And I can add my RA in here. So let me change the color to this and add RA right here. And then ask, does anything change here? So before we add the RA, we wrote a KCL. So this current and this current have to be equal and opposite because they have to add up to 0. But now I have this RA. Does this RA change anything here? All right, well, the op-amp says, regardless of what's happening in the circuit, I want these two voltages to be close to each other. This is still a virtual ground. So if this voltage is 0, this voltage is still close to 0. So this voltage is still close to 0. So that means that Vx here is still close to 0. If Vx is close to 0, how much is the current through RA? Close to 0. So we can say with a good approximation that this current and this current still have to be equal and opposite. So this KCL still holds because the current through RA is negligible because the voltage across RA is very small. All right, so we say KCL still holds because Vx over RA, so this voltage here, right? This voltage divided by this resistance, so the current through RA is small. So we don't have to include that current in our calculations of a KCL here. All right, so interestingly, if we connect a resistor from the virtual ground to the ground, the overall equation doesn't change with the assumptions that we have made so far. Of course, if RA becomes really, really small, some other effects have to be considered, but at least for now, that's what we have. Okay, so this concludes our study of the inverting amplifier. I will see you next time.